For invitation to come to this splendid event and celebrate with Leon. It is his birthday, and what I'll speak about combines some of his interests, in particular random matrix theory and statistical mechanics, and brings in one which I'm hoping will become his interest, which is number theory. So what I'll be doing is basically discussing the manifestation of the freezing transition that was discussed beautifully yesterday in Anti-Kubinen's talk for random matrix theory, and then conjecturally, highly speculatively, for the Riemann Zeta-Function. So what I want to do is try and outline the connections between these subjects and why we think they're worth studying. So the problem's the following one. Let U be an n by n unitary matrix. So its eigenvalues lie on the unit circle. And let's consider the characteristic polynomial of this matrix. So this is the determinant of I minus u e to the minus I theta. So this is the function on the unit circle as a function of the angle around the unit circle. It's the function of theta which vanishes whenever theta hits one of the eigenvalues of the matrix U, and I'll denote this Pn of U and theta. And for several years now, people have been interested in the distribution of values taken by such a characteristic polynomial as one allows U to vary through the unitary group. As one draws U from the circular unitary ensemble of random matrices as defined by Dyson. And there's just as a remark, that's a problem that really grew out of a program that started here in 1997, where our chairman and myself were two of the organizers. The main result we have here is that if one looks at the modulus of P, modulus of the log of the characteristic polynomial, and normalizes this by the square root of a half log n, n is the size of the matrix, it's the number of eigenvalues, then in the limit as n tends to infinity, the values of this log of the characteristic polynomial normalized in this way become normally distributed with mean 0 and variance 1. And that's a theorem that Nina Snaith and I proved about 10 years ago.
Absolute value, not absolute value.
Oh, yes, you're right. Sorry, yeah.
Speak up. Next time, speak up.
So this fixes, if you like, the typical size of a characteristic polynomial. Typical size, if you like, is roughly square root log n. What I'll be focusing on today is not the typical values of the characteristic polynomial, but rather the maximum values. So if we define P max of U to be the maximum with respect to theta of the modulus of P. So this is now a function of the matrix U. As you draw U randomly from the unitary group, what's the distribution of values of P max? So what is the typical size of the maximum of a characteristic polynomial, and what are the fluctuations around that typical size? And what I want to argue is that this problem is related to the freezing transition that we heard about yesterday. The kind of motivation, or an insight into this, if you like, a way of thinking about it, is the following, which I'll mention sort of as a parenthetical remark. If you draw the modulus of the characteristic polynomial as a function of theta, it looks something like this. it has n local maxima, because there are n zeros of the function. And if you assume that the values of the local maxima take on the normal distribution of the typical values, so if we assume that the values of these local maxima themselves satisfy that same normal distribution, and if you assume they're independent of each other, then you can write down what Pmax should be. It should be log n minus a quarter log n plus some fluctuating term, which is of order 1, and the probability distribution of values of x is d by dx e to the minus x. This is the Gumbel distribution that was discussed yesterday. And the 1/4 there is important. So I'll come back to that this a little later. So this is what you'd get if, as I say, you treated the local maxima as statistically independent from each other and with values coming from the normal distribution. Now, what's the motivation for studying this problem? Well, one motivation comes from number theory. So let me explain that. And this is associated with the theory of the Riemann zeta function. So the zeta function is a function of a complex variable s defined by a product of prime numbers, or a sum over the positive integers, has an analytic continuation in the complex plane, and there's a famous problem associated with the zeta function, and this asserts, the hypothesis of Riemann, that the zeros of this function, when you continue it into the complex plane, the zeros that don't lie on the real axis all lie on a straight line in the complex plane. And this is the line with real part 1/2. So this is the Riemann hypothesis, which is a very famous problem in pure mathematics. This means that the line with real part 1/2 is an interesting line, and one can ask, what are the values of that function? So as you vary t, as you walk up the critical line, how are the values of this function distributed? In particular, what are the maximum values it takes? If you look over some range, and you specify the range, what would you expect the largest value of zeta to be? Well, it turns out in the number theory world, this is a hugely controversial subject. There's a famous conjecture of Lindelof, goes back about 100 years now, which asserts that this function grows more slowly than any power of t. So it grows more slowly than t to the epsilon for any epsilon that's positive. And that's a very important conjecture in the world of number theory. There are more quantitative versions of this. If you assume the Riemann hypothesis, you find, so on the Riemann hypothesis, this will be order e to some constant times log t over log t. So that's a quantitative version of that statement. And so the question is this an accurate measure, is this an accurate bound on the maximum size of the zeta function? And there are wildly differing views in the number theory community. Some people believe that the zeta function does get this big as the Riemann hypothesis allows it to get, and there are others in the community who think it gets only attains much smaller values than this. In particular, they believe a bound more like e to some different constant times the square root of log t over log t. So in the natural variables, these are exponentially far apart. So it's a very controversial subject. And the question is, can we shed any light on this using random matrix theory? Well, why would we expect to? What's the connection between the two areas? Well, the connection's a conjectural one, and it's that conjecture which goes back to Hugh Montgomery. It's that the zeros of the Riemann zeta function, their heights at the critical line, are correlated in the same way as the eigenvalues of a random matrix U. So if I denote these eigenvalues e to the I theta n, that the heights of the Riemann zeros are correlated like the eigenphases theta n. In particular, this is true, believed to be true, if you normalize the zeros and normalize the eigenphases by their mean density. So these quantities now have on both sides mean density 1. So it's believed that in some statistical sense these numbers are correlated in the same way as these numbers, and we know how these numbers are correlated from random matrix theory. So the kind of philosophy that comes about is that if the zeros are correlated like the eigenvalues of a random matrix, perhaps the zeta function, the values of the zeta function, are correlated or distributed, if you like the values of the function which vanishes at the eigenvalues, and that's characteristic polynomials Pn. So if we can understand the maximum size of characteristic polynomials, the hope is that will shed some light on the maximum size of the zeta function. What's the specific question one might hope to shed light on? Well, since matrix size is related to the log of the height up the critical line, so the two parameters that come in, on one side one has the mean, in both sides it's the mean density of zeros and eigenvalues, and if one associates these two parameters, one would associate a matrix size with a height up the critical line, and so basically the matrix size is the log of the height. So the picture that emerges is that one gets the Riemann zeta function on the critical line, splits the critical line into sections of length 2 pi. So each section of length 2 pi. Such a section of the critical line on average has log t zeros in it, and so that will be identified with a matrix size n. So the idea is that each section of length 2 pi of the zeta function, in some philosophical moral sense, should be related to a different unitary matrix. And so if one averages over a long range up the critical line, one's averaging over many unitary matrices, hence one might expect random matrix theory to govern such averages over long ranges. If we're going to look at the maximum of a given characteristic polynomial, the hope is that would tell us about the maximum of zeta over a short interval like this. So if you find zeta max t to be the maximum over some range between capital T and capital T plus 2 pi, and view this as a random variable depending on the height capital T, the hope is that the maximum of the characteristic polynomial would tell us about this distribution of this random variable. So that's the motivation. Now, is there some basis for this? Well, yes. There's a lot of evidence that this relationship is correct. In particular, the log of the zeta function satisfies a central limit theorem. It's a theorem of Selberg in the 1950s that's exactly the analog of this central limit theorem if you replace n by log t and p by the zeta function. So this same heuristic picture that I've drawn at the top there, if you assume that the local maxima of the zeta function are uncorrelated, and if you assume they're governed by that central limit theorem, you'd expect to get the same behavior for the maximum of zeta, where here one replaces n by log t. So that would be the consequence of that model. The problem is, in both cases, for the characteristic polynomial and for the zeta function, one knows that this independence doesn't hold. And here's where we start to make a connection with the talk of yesterday. So if one defines VU of theta to be the log of the mod of the characteristic polynomial, then VU has a non-trivial autocorrelation you take the limit as n tends to infinity and look at this for small values of x, this behaves like minus a half log mod x. So characteristic polynomials, the logarithm of the characteristic polynomial are log correlated. That is, there are long-range correlations. So this model of treating local maxima as statistically independent is highly questionable. And exactly the same holds for the Riemann Zeta-Function. If I if I define v zeta of t to be the log of the mod of zeta of a half plus it, and replace the expectation value here by an average up the critical line, you get exactly the same log correlation. So the question is, do these log correlations affect this sort of guess that I've written at the top there? Are they sufficiently strong to influence that formula? Well, here's now where we make the connection with statistical mechanics. So how might one analyze this problem? And now let me focus for definiteness just on the random matrix problem. So what one might do to analyze the maximum of the characteristic polynomial is to compute the moments and hope to deduce the maximum value taken from the moment. So if we define z of beta u to be 1 over 2 pi integral from 0 to 2 pi modulus t if so z beta u is the beta power of the characteristic polynomial, we can recover the maximum simply by taking 1 over beta log z and looking in the limit as beta tends to infinity. So the log of p max. So one can uncover the maximum value if one can uncover the dependence of this function on beta in such a way that one can take the limit as beta tends to infinity. So what's the connection with statistical mechanics? Well, it's pretty obvious what one might do here. One writes this as 1 over 2 pi integral from 0 to 2 pi e to the beta vu of theta, and then tries to interpret this, this is z, tries to interpret z as a partition function for a statistical mechanical problem where one has an energy given by a potential energy vu of theta. So now we connect with problems where one wants to understand statistical mechanics of landscapes given by some potential energy function, and one wants to understand how the behavior of the partition function might depend on the structure of the landscape. So what does this landscape look like in the case of a characteristic polynomial? Well, vu of theta, defined above, it's the log of the mod of the determinant of I minus u to minus I theta, which you can expand as a Fourier series with coefficients So it has a Fourier series expansion for this potential in the random matrix case. And it's then a theorem of Diaconis and Shashahani that these quantities, trace u to the n over square root n, in the limit of large matrix size, satisfy a central limit theorem. They're like random variables with a normal distribution. So this potential that appears in the random matrix problem, this potential energy, looks like a random Fourier series. So one should think of this as each matrix gives rise to a potential energy function, it's a function of theta, which is a very complex function. It's a disordered function, if you like, of theta. So this is like the problem of statistical mechanics for random landscapes. Now, as I've emphasized, the random landscapes that appear here are log correlated.
One particle in a random landscape.
Yes, yes.
The different n are correlated or not correlated?
In the limit, so if you fix n, they're uncorrelated. There is a subtlety about the uniformity of that limit. So the result I stated from Diaconis and Shashahani is you fix the power and then take the limit of matrix size tends to infinity, and then they're uncorrelated. So that's not the same as fixing the matrix size and letting the power n tend to infinity. There's a subtlety in that, in the uniformity. So the problem looks very similar to the problems we were hearing about yesterday, where we have a random landscape given by some sort of random Fourier series, which is log correlated. And there, what we heard yesterday was, in these problems, one expects a freezing transition, and the nature of the freezing transition. So the existence of a freezing transition is pretty robust. It doesn't depend on the nature of the correlations, but the actual structure of the freezing transition does depend on that. So if there were no correlations, the VU of theta were uncorrelated, this would be the random energy model that we heard about yesterday. The presence of these log correlations we heard yesterday affects, influences the expectation one gets for the statistical mechanics, and one may expect the same phenomenon to appear for the characteristic polynomials, and hence by conjecture, association, for the Riemann Zeta-Function. So how does this actually manifest itself? Well, first of all, you can see roughly what's going on, in that you can think of this as a section cut through the Gaussian free field. So this is very much like the problems we were hearing about yesterday. However, in this case, the problem kind of is auto-regularized. The structure, or the determinantal structure here, regularizes the problem, so the issues arising when one tries to analyze the Gaussian free field case don't arise here. The regularization's built into the matrix problem. So how does one analyze this? Well, one looks at the moments of Z, and the goal is to try to analyze the moments of the partition function. If we know enough about the moments, one should be able to invert the moments to determine the value distribution of the partition function. Then I repeat, if we know the value distribution of the partition function, we can recover the distribution of the maximum value, P max. So this is, you can write explicitly. Simply by writing Z as an integral over P, and then taking the kth power of that integral. If you take the expectation value inside the integral, this is something one can evaluate, the expectation value of products of characteristic polynomials. One can calculate from Fisher-Hartwig. And this kind of term looks itself like a Vandermonde. That's the power minor beta squared over 4. And then this integral that one's left to do over the angles looks like a Selberg integral. So this gives you, allows one to evaluate the moments of the function that looks like the partition function. From the moments, one can invert and get the value distribution of z in the limit when beta is very much less than 1. But one needs to invert, in order to invert the value distribution to get the maximum, one actually needs to set limit as beta tends to infinity. And the obstacle is there's a singularity at beta equals 1. And this one wants to interpret as some sign of a freezing transition, and the nature of the singularity is the same as found in problems where the freezing transition has been analysed. So if one assumes that that freezing transition does affect the behaviour beyond beta equals 1, that is, these moments, their values freeze at the beta, as one takes the limit beta tends to infinity, they actually freeze at the beta equals 1 value. That allows one to invert and so get the distribution of the maximum. And the form it takes will be familiar from the talk we heard yesterday. So log p max of u is like log n minus 3/4 log n plus a random variable of order 1, and the probability distribution of this random variable is like 2 e to the minus x k0 2 e to the minus x over 2. So we have an explicit formula for the fluctuations around the typical size of the maximum. And the things to draw out are, first of all, exactly as we heard yesterday, the term here compared to the random model is multiplied by a factor of 3. So it seems that that phenomenon that we heard about also manifests itself in characteristic polynomials, and this is believed to be a universal feature of these log correlated random landscape problems. And in fact, this has now been much better understood by Jan Fyodorov and his co-workers, and one sees this as related to the structure of the multifractality of the measures that underpin this kind of these kinds of distributions, and I'll say a little more about that in a minute. So there is this kind of universal coefficient that appears, and again, as we heard yesterday, one has a distribution for the random variable, and in this case, the tail of the distribution is exactly like the universal form that that we heard about. Rather than going as e to the minus x, it goes as x e to the minus x, as x tends to infinity if you put in the asymptotics of the Bessel function. So, in the world of random matrix polynomials, it looks like the phenomena that underpin associated with freezing in the statistical mechanical problems we heard about yesterday also show themselves, and that freezing determines the large values of characteristic polynomials. So one might therefore conjecture that freezing will in the same way fix the large values of the zeta function over such ranges of length to order 1. And that this distribution that one finds over there will also appear in the zeta function. And the early indications, a great deal of numerics has been done for the zeta function, and the early indications comparing to data that have been obtained by Guy Hyrie, who's the kind of Large Hadron Collider of computing the zeta function. He's able to go many orders of magnitude beyond where other people can compute. And the data he's produced so far are certainly supportive of these connections. So sort of speculations that one might write down, extending this formula to the zeta function by identifying n with log t seem to be borne out by the numerics so far. So it does appear that large values of the zeta function freeze in the same way as we've heard it in these other problems. Now one can take this analysis further. So I focused on looking at intervals of length 2 pi for the zeta function, or for the characteristic polynomial case, looking for the maximum of the characteristic polynomial all the way around the unit circle. One could instead replace this by some arbitrary segment of length L. So ask for the maximum of the characteristic polynomial over a range of length L, not the whole unit circle. And likewise for the zeta function, one can look at the maximum over shorter intervals of length L, where L scales in some interesting way. And one can follow through that analysis in a rather similar way to I've indicated here. And what one finds there is behavior that's rather reminiscent of this behavior. So this appears to be robust. It's not a special property of averaging around the whole unit circle. It's reasonably robust. But what one finds is that the moments of the partition function have a very non-trivial scaling in terms of L, and that's indicative of multifractality. So it appears that the characteristic polynomials share this multifractal property, that the moments scale in a very non-trivial way, depending on the length of the resolution one analyzes them over. And so again, conjecturally, one might speculate that the large values of the zeta function similarly show multifractal behavior. And I think that's a possibility which would be extremely interesting to explore and would be a completely new idea to the number theoretical community. So this work, which is joint with Jan Fyodorov, who's here, and to some extent in terms of the numerics with Guy Thyre, I think what it does is indicate some interesting connections between these problems. I think the connections between random matrix theory and statistical mechanics are interesting. There seems to be a new example of the kinds of general freezing phenomenon that have been studied in recent years for random landscape models, but maybe not altogether surprising, useful and interesting to know. I think that the connections with the zeta function, if they're true, would be really rather interesting and would introduce many new ideas to the number theoretic community, which I suspect it will take them several hundred years to sort out, given that we can't even sort out the Riemann hypothesis. So I think that's what I wanted to say, and I think I've left us some time for questions.
Thank you.
Yeah. So the statement about the log correlation of the log values of the zeta function, is it the theorem, or
yes,
where is it coming from?
It comes. Do you mean how do you prove it?
I mean when it was proved by whom? And
okay, so there's a complicated.
Selberg's theorem is not about this.
Selberg's theorem is not about this. In recent years, there's been work of Paul Bourgade, Mark Ure, for example, got interested in this and started to look at multi-dimensional versions of Selberg's theorem, essentially.
Multi-point correlation functions?
Exactly, that sort of thing. Now, I'm piecing together, in making that statement, I'm piecing together different results, because they don't always write them in exactly this way. But there is a whole body of people who've now started to think that if you piece together their results, you get that. It's not difficult to show. I mean, you can calculate the correlations. They're not difficult to calculate. This isn't not terribly hard theorem, actually.
Just 1 second. Yeah. I want to ask, so you expect three quarters to be true for number theoretical setting as well?
Yes.
Would you expect the limiting law for the correction is also be the same?
Yes, and the numerics for 3/4, I would say, would convince pretty much anybody. Someone's tested the 3/4, and that's pretty robust. The numerical data for for the fluctuations are certainly supportive of this, but not compelling evidence that it's absolutely correct.
Yeah, now the multifractality holds only at the transition or around it or everywhere?
Well, the transition determines the multifractality, I'd put it that way. The multifractality, there is no beta. There's no, one's taken the limit as beta tends to infinity to get the value distribution of the function. But the claim is that the transition determines the beta tends to infinity limit, and so determines the value distribution, which is multifractal. By multifractal, I mean that one doesn't look just at the maximum value, one looks close to the maximum value and sees how that scales.
Yeah.
Just two short comments about multifractality. Is just no, it's for any beta. In fact, multifractal just the moment scale non-trivially with lengths of the interval that you consider. They scale with these powers which are typical for basically the Gaussian logarithmically correlated field. So it's everywhere. It just should take small intervals and then they scale. It's small comment. Now, second comment that, okay, my general understanding that this formula we expect to be exact for characteristic polynomials, but for Riemann zeta function, our general understanding that universality will hold for left tail,
yes, yeah.
But it's open question whether it's, in fact, I personally doubt that just literally this distribution will be, but it may be very close to actual distribution.
Yeah, maybe that's a more careful way to say it. What I said was one believes something like this holds, and that the numerical evidence doesn't suggest this is wrong, but whether it's something, whether it's exactly that or something like it. I mean, this connection is complicated because the values of zeta. These are not local statistics. Yes. So whenever one does this, one has to build in some arithmetical information, which I've not spoken about here. We believe that doesn't determine the leading order. As one goes infinitely out the critical line. But that remains to be completely resolved.
This is the same question which I have in mind, that you know that for distribution of psi function of negative curvature models, there are points where they are anomalously large, so they are not given by a random matrix. And these points related with the points where infinite number of periodic orbits cross. So contributions from arithmetics may be also of importance for us, especially for random matrices usually give you average characteristics. So local characteristics may be sensitive to arithmetic structure.
You're right, it's a very delicate issue. I mean, the reason why one might speculate that arithmetic doesn't affect the leading order asymptotic is a subtle one, an interesting one. It's that we know how arithmetic affects these moments. So the moments of Z, we know how arithmetic will appear here. It'll appear as some factor that depends on beta. It so happens that the arithmetical factor at beta equals 1 is itself identically 1.
Okay.
So that's a sort of indication that it doesn't affect the leading order asymptotics in my view.
More questions? Then we can take your point. This is a delicate issue and end the session. Thank you.
Okay, I need to make an announcement.